Okay, guys, gravitational field. So, anybody? What is it? Any idea? What is gravitational field?
Like
Yes.
the extent, so like the extent to which particle or a body can like attract.
Yeah, very good. If there's a body having some mass, what we call as mass, everything is debatable now. Okay, what is mass and everything? But we'll just consider classical physics, Newtonian physics, and talk in those terms. Okay. So this mass is supposed to have a certain aura around it, or it has got a certain field around it. Okay, in which it can have its influence. Okay. This influence has been studied by Newton in a certain way. It has been studied by Einstein in some other way. You already know it, bending of the time and space curve. Now, in terms of Newton, he has given a very simple, through a very simple observation. What is that observation? Not the falling of an apple. It is the observation of uh, looking at the sky. Obviously, long before him, also people know that things are going around the earth. So, moon is going round and round the earth, and this guy Newton lives on earth. He's pretty cool with his physics and all. So he knows that if a body has to go around something, then there must be a string attached. I would say string attached, which is pulling the body towards the body around which it is going. There has to be a centripetal force, right? Right, guys? mv square by r centripetal force has to be there, without which it will not, it will keep on going in a straight line and will not curve, it will not bend. Okay, if the bending has to be exactly circular, the force has to be exactly this much. Is that clear, guys? So if you are seeing a moon in the sky, you would really wonder that how it is going around the earth if there is nothing attached. So we figured out that somehow a mass must be attracting another mass. Without the string attached, there is a force. And he put a law which is universal. He got it from Earth and Moon or other bodies, other celestial bodies. It can be applied universally. So, what is the law? The law is F is equal to, or F is proportional to one mass, it is proportional to the other mass, it is inversely proportional to the square of the distance between them. Bigger are the masses, more is the attraction, bigger is the separation between them, between the center of masses, bigger is the separation, lesser is the attraction. So this is, the force is given by this equation, right? So if you remove the proportionality, you put a constant which is called universal gravitational constant. So that constant is applicable on for any pair of mass. So that's your law. Any doubt about it? Any doubt
No,
about
sir.
it? It is amazing that we could figure out, we are so developed that we could figure out G using experiment in the lab itself. Like very precise experiment where, say, one bob is suspended, another bob is suspended, okay, then it should be totally vertical, right? The lines. But if there is attraction, what is going to happen? It is going to come this side and that is going to come that side, right? Right? Then by measuring the angle, how much it has moved, you can actually figure out the force. And how much is the force? So you already know the measure of the masses. Mass 1, mass 2. You know the separation between them at stable condition. Right? So you know the angle, so you can figure out the force, and hence you get your G calculation, right? The G calculation is actually doable with bodies which are like not as massive as Earth and Moon and all. You can still do the G calculation. Anyway, so this is about the formula, the universal formula for gravitational attraction between two masses. Is that clear? Now comes field. What is field? Okay. So the point is, if this is a mass, say m is the mass, then whether you keep another masses around it or not, it has got influence around it. Okay, so we say there is field lines. These are not actual lines and all. Okay, it is a way of imagining. And make more this side because I will writing most of it on the right side. So it's a way of imagining. Okay. I think I'll need even more lines on the sector. So now, if you keep a mass, if you keep a mass, say m, in the region around that, then this mass definitely doesn't have eyes. That I'm seeing this big mass n and hence I should start moving. It doesn't have eyes. But something invisible is crossing that mass. Like something is some field is crossing you also at this time. Those fields are called gravitational field. And this mass will be forced in the direction of the field. Is that clear? Is that clear? Meaning to say, like suppose the big mass m was somehow able to create a field line of this shape. Suppose. Okay, field line of this shape. And if I keep a mass over here, where will this m go? Will it go directly to this? No, it will not. Why? Because it doesn't see that thing. What it sees or what it feels is the field line crossing. So where will this mass go? It will follow the line, it will follow the brown line. Is that clear? Is that clear? Is that clear?
Yes,
Green point? Okay. So every mass creates the field line, and any other mass kept in somebody else's field line will experience the forces due to the field line. So those field lines also were called lines of forces. These were also called field lines of forces or lines of forces. Okay, this is the field. Is that clear? So field lines of forces you can call them. Okay, why? Because the force is in this direction. So what is the strength of the line over here? We will denote by a letter E, which means gravitational field. Okay, the intensity of the gravitational field. Suppose it is E. So more intense is the field, more will be the force. So what is the force? Force is on the mass m, and how much of field line is crossing it? Exactly in the direction of the field line. So do you understand this formula fully? If not, you tell me. It's very, very important. Okay? Or I'll repeat. You understand the formula?
So E is like an acceleration.
Yeah, so it will ultimately come as acceleration unit. Okay, unit wise. Unit wise, it will come as acceleration. because the same guy gave another thing that force is directly proportional to mass into acceleration. Okay. And then he proposed his own name as a unit. So if you keep one mass and the acceleration is 1 meter per second square, meter was already defined, second was already defined, so you get a force. Hence you get a force, and 1 kg was already defined at that time, so you get a certain force. Now you have to match that force with this formula of G mm by r square. Therefore, such a weird value of G, because that unit has to match this unit. Okay. So G got a massive unit. Okay. Anyways, you don't have to get into the history and all, which is quite interesting. Okay, you can read it separately, but what I'm trying to say over here is that I hope everybody understood that, but still I'll repeat it if you haven't. That any mass has got a field line around it. That field line over here would be directed towards the mass. Okay, if it is a mass of the shape which I have made, it is directed towards the mass. The strength of the field line is given by a letter E. Now, what we can't see it, how do we feel it? If some mass is kept over there, some other mass, m dash m, then that mass feels a force. That force is given by F is equal to the mass kept into the field line E. And it is exactly in the direction of the field line. Is this part clear, guys? Everybody? Is this part clear?
Yes, sir.
Now, suppose the distance between them is equal to, very basic class I'm taking. If you want to teach me a little higher level, you in the polls, I will actually ask the level also, low level or high level. Okay, but these classes are for low level. Okay, basic level. So that you can build on that. If the distance between them is r, then we also know that the force is given by what?
G m by r square.
M by r square. So from here, you can just imagine what is the field line given by, how much is the field strength of the field given by, or intensity of field given by. They use various words: strength of field, intensity of field, just field. Okay. How much is the field?
G capital M by r square.
Gm by r square.
Me. So it is G m by r square. There is no question of the other mass. This is field created by this big mass, right? That's very clear from the formula itself. That you go further, my field strength is low. You come close to me, my field strength is very high. Is that clear, guys? Is that clear?
Yes, sir.
Yes.
Yes, sir.
Yeah. So now next concept comes on this. Very simple concept, okay? Very, very cheap thing, okay? If I have a body, say this is Earth or any other planet, okay? Planet or satellite or whatever. I have a body, okay? And I leave the body. What happens? What happens?
The body moves towards
Let
the
it
planet.
go. Huh? Yes, what happens?
The body moves towards the planet.
Yeah, it falls down, right? Yes. Okay. Now, if I ask you, why does it fall down? Why does it not stay there? Why does it fall down?
Because there's an attraction between the body and the planet due to the force of gravity.
The planet, absolutely right. The planet will have field lines towards it, right? Right? The whole space will be filled up of field lines towards it. Okay, field lines are crossing this guy also. So the strength of the field line crossing this guy, okay, lines are just representation. Okay, I can make 10 lines crossing it, I can make one line crossing it. Don't make it 10E or something. Okay. So if the field line is crossing it, then there is a force on the mass in the direction of the field line, which is F is equal to ME, and is going to go in the direction, and hence it is falling down. That's the precise reason, right? Is there any other way of stating the same thing? The other way, which I really felt a stupid way of stating things when I was at your age and all, that the mass always goes from higher potential to lower potential energy. Mass always wants to reduce its any body automatically goes towards it, the lower potential energy level. Okay, that's the natural thing to do. And I used to feel, what the hell? Is the body a human or something that I want to go towards this? So the answer of it is forced downwards because of field line is a better answer for me. Okay, but anyways, the other answer is also very popular. What is that? If I leave a body, say on Earth, and let it go, why does it fall? Because it goes from higher potential energy to lower potential. So the term potential energy now comes into the picture. Is that clear? Is that clear, guys? Is that clear?
Yes.
So what we can all agree at this moment is that if you go along the field line, are you going to increase? Is the body going to increase in potential energy or decrease in potential energy?
When it goes down, it decreases.
It decreases, right? So it naturally falls down. It naturally falls down. So naturally, wherever the body goes, which we say it wants to go towards that, it is actually forced by the field line. So this is the lower, and this is the higher potential energy of a body kept. And if there is no body kept, then the term potential comes. Now let us explore the term potential. Is that clear? It's not same as potential energy. Is that clear? Okay, so let me come back to this diagram over here. And just to be away from the other formula what I've written. Okay. So everybody agrees at least on this fact. If not, then you ask me. Okay. If I say everybody, don't get into under a pressure that everybody knows I'm done. This time is for you to speak and ask if you don't get it. Okay. Take it as your last chance of understanding something, at least by Neev classes. Okay. Then there are a lot of other help that is there. Tuition teachers are there. Online videos are there. This and that. But if you try to get help from here, one is at least you'll get the right stuff. And secondly, there is a long engagement, 1.5 years more of engagement. So if you build a habit of asking the doubts, that is really going to help. Okay, so I think everybody agrees on this thing that if I keep a M mass over here, it is all automatically going to go down towards the big M mass and come over here. This potential energy will be higher. We call it as U. U is high. And this potential energy will be lower. Right? U is low. Guys, you agree on this part?
Sir, I am not like 100% clear with this potential topic.
Okay. So this is how it is defined. It's a new term, no? Potential energy or potential. Okay. So I'll again say, if I was over here at this position, and I leave the mass over there, the green mass over there, what is going to happen to the green mass?
It's going to fall towards larger mass.
It is going to experience the field lines. Okay. Whoever has created it doesn't even know. Okay. It is going to experience the field line. Field line strength will be given by this formula. Okay. And it is going to go along the field line because there will be a force which will be along the field line, right? Right?
Yes, sir.
So do you agree that naturally it is going to go from here to there? Is that okay?
It wants to go from a point of higher potential to a low potential.
Yeah, but forget about potential. Do you agree that it is naturally wanting to go from point 1 to point 2?
Yes, sir.
Yes, sir.
Yeah, so we are now introducing a term potentials that a body naturally attains or wants to attain lower potential energy. Okay, or it naturally goes from a higher potential point to a lower potential point. Okay, is that clear? Is that clear? Where a body naturally goes, okay, that means due to the gravitational forces where it goes, that is called a lower potential point. Is that clear?
Yes, sir.
Is that clear? In the point? And
Got it, sir.
okay, so now, do you also agree that had it not been m mass, it was some other mass? It was a 3m dash mass, okay, 3m mass, which is m dash, some other mass. That would also go from here to there, right?
Yes, sir.
It is not about that mass. It is like anybody kept over here will go from here to there, right? So instead of defining potential energy for the masses, we define something for the spot itself, okay? So we define something for the spot itself, that this spot is something higher than this spot, and that something is called potential. What is it called? Potential. Is that clear? Is that clear?
Yes, sir.
Yeah, like there is a certain coaching institute, okay? If you are there in that coaching institute, you are having a higher potential. You are having, you are having a higher potential energy. That means you are having that energy due to the virtue that that coaching institute had some space in that coaching institute, the spot in that coaching institute had some potential. I really messed it up. Okay. So I'll just speak in other terms. Okay. I just wanted to bring in Neev classes and all. But I hope you are understanding. Coming back to the actual real thing, that space is having a potential, and we are yet not saying what is potential energy. The potential energy is, if I keep a body over here, say of m mass, then that m mass will have potential energy. Is that clear? So there are two
Yes.
different things. Anybody is not understanding the difference between the two, please ask me.
Sir,
Anybody?
understand.
If you want me to
Potential
repeat, I'll
energy.
repeat. If you have understood, don't speak up. If you have not understood, I'll repeat. Anybody? Not understood? Not understood? Anybody has not understood? Okay.
Sir,
So the space over here is having a potential. That space was having a potential due to virtue of this big mass present. If the big mass m was not present, the space will also not have a potential. Got the point?
sir, but what is the difference, sir?
1 second, guys. तो बोला था नहीं बंद करना है. सुबह दे देगा. ठीक है. अच्छे से रख देना गाड़ी को. ठीक है. Yeah, guys.
Sir, I didn't understand the difference between potential and potential energy.
Yeah, that is what I'm asking. Did you understand or not? We have not. Okay. Anyways, I'll repeat. Did you understand the difference between field and force, E and F? Yes, no.
Yes, sir.
Sure. Yeah, what was it? What is the difference between E and F? Tell me, whatever you have understood, it's okay.
Sir, E is the acceleration or the
No,
E is like the acceleration that is given by
not at
field.
all. Not at all. Not at all. That is what you were all planting that time. It comes out to be acceleration. If a body is left, that is a different story. Like field is right now crossing you. Are you accelerating? Right now you are sitting, is gravitational field properly? Is it giving you any acceleration?
No, sir.
It could have given, but when you're not sitting on the seat and you are really having a free fall, okay, that's another story. The force can give acceleration is the third story, given by again the same person. Okay, but what is E? Tell me properly what is E? I'll repeat what is E. There is a mass, it has got influence around it. Okay. Okay. Influence to force things around it. Things means another mass is around it. Okay. Farther you are, lesser is the influence. Closer you are, more intense is the influence. Okay. So it is called field intensity. Is that clear? Is that clear?
Yes, sir.
That is given by, naturally it is given by the formula. Some constant, you don't have to worry about it. Okay, since we are talking about gravitational field, it is gravitational constant. How big, how heavy, sorry, how massive the mass was. What was the mass? Okay. So obviously, bigger the mass, more the mass, higher is the influence. Okay. And farther away you are, lesser is the influence, right? Right? So that much far away. Is that clear? This is the influence you feel. Now, this influence has got a direction also. If you have to write in the terms of direction and all, we write in a very crazy way, but you don't have to write that way. R cube and negative. Why we write this way? Because the direction is in the direction of the R, right? And R is measured from the mass to that spot, but the field will be in this direction, so minus R vector. So you don't have to worry about this part, you just worry about this part. That is your field. Isn't clear? Every mass has got a field. Now, how you will say that how do I believe that this mass kept around it is having a field? How do you test it? How do you test it? You don't believe that there is a field over here. How do you test it? You keep a mass over there, some other mass. And then what happens? It experiences the force. Is that clear? Is that clear?
Yes, sir.
So force is the test of the field. Is that clear? If you kept double the mass, the force felt would have doubled, or it actually doubles. If you keep triple the mass, then the force becomes triple. Okay, that means this field is not changing. The influence at that place is not changing. Force is changing just because of the virtue of the mass kept over there. Is that clear? Is that clear? So the influence is actually measured through the force itself. Higher the force is felt by a test body, so we can say the test body is 1 kg body. Then the measure of the force is actually the measure of the field if the mass is 1 kg. Is that clear? That is like a test mass. Okay? Is that clear? Is that clear? But had the mass been 2 kg, the force would have been 2e. Had the mass been 3 kg, the force would have been 3e. So the force felt is kind of a measure of what is the field over there. Is that clear, guys?
So E is like the strength of the field.
Yeah, the strength of the field. E is like the strength, E is the strength of the field, man. Is that clear?
Yes, sir.
The point is, if I have no test mass over here, there is no force to be applied on anything. But there is field. Is that clear? Similarly, this spot is having a potential, the letter V, potential. Just because it was in a environment or it was near another mass, at this point has got a potential. Now, how to understand how much is the potential? To understand how much is the potential, we say that if there was a mass over there, M, then this mass would have gained a potential energy. And measuring potential energy is easy, I'll come to that. This mass would have gained a potential energy. And that is proportional to how massive is the mass, whether it is a 1 kg mass or a 100 kg mass. Like if you can see me, this is a walnut over here. At this spot, it has got a certain potential energy, right? And I keep a very heavy, this thing is full of mud, soil. So it is really heavy. Okay. So this thing is also having a potential energy. Are the two potential energies same? No, not at all. Okay. But this spot over here and here was having the same potential because it was created due to the presence of the earth. Is that clear? Had I kept another walnut over here, then this walnut and that walnut would have got the same potential energy. Is that clear? Is that clear? So the space over there is called potential, and the body, if you want to keep a body over there, then the body will attain a potential energy. So that potential energy is given by M into the potential of the space. Are you understanding?
Yes, sir.
So most definitely the potential alone will have nothing to do with small m. So if we calculate and all for the given mass, it comes out to be minus gm by r. That is, like formula sake, it comes out to be that, which we can derive very easily. But I hope you understand the concept that V doesn't care about what mass you are keeping over here. Okay, and U is obviously talking about the mass kept over there. Is that clear, guys?
So what is the relation between V and E?
Yeah, we'll do that. But have you understood what is V?
Yes, sir.
Yes, people understood what is V?
Yes, sir.
Okay. So I've written the pink spot is the potential, and a blue body kept attains a potential energy. Excuse me. Now we know that we were saying a body goes from here to there. It will move from, say, higher potential to lower potential because of the field line presence. Okay, the body goes from higher potential energy to lower potential energy because of the force of gravity. That's the actual story, right? So obviously, we can have a relation, like the other guy was asking, what the relation? We can have a relation between the potential and the field. We can hope to have a relation between V and E, right? Right? So let us just create a relation which you may say that what the hell is that? What is it? Okay, it can be wrong also. That can be definitely wrong. But we'll come to the other way of doing it, which is definitely right. You tell me if this pink line which I have drawn is longer, then the change in potential will be more or less. In the pink line, if I say I'm talking about this spot, from this spot, I'm talking about this spot. Is the change in potential more or less? What do you think? Like a body is going from here, if you can see me here to there, versus here to more down, which is having more change in potential energy of the body. Or if I talk about the spot alone, then here to here is a greater change, or here to there is a greater change.
So from up to like more down is greater change.
Yeah. So change in potential will one depend on how far you are going along the field line, and is definitely going to depend on the field line. Is that clear? Is that clear?
Yes.
Okay. So had it been a very happy, very easy situation, what is the easy situation? Easy situation means yeah. If my field lines don't change, if my E value doesn't change, here also the E is same, here also the E is same. That means if I keep a mass over here, the force felt will be F is equal to ME. And if I keep a mass over here, then the force felt will be F is equal to ME again, same E. Is that clear? If E is same, then my change in potential is quite simple. E into whatever distance I'm doing. Say X, then X. So generally we say H, then H. Is that clear? Is that clear? I'll come to a certain thing, but I'll try to relate it later on. Right now it may sound a little surprising. For Earth, the field line which is near to the Earth is written by the small letter G. Instead of E, we write G. Okay. And we also call it as acceleration due to gravity, which again I'll explain why we call that. We call it as G. Is that clear? And according to this formula, if I go H down, then how much is the change in potential? I've gone to a lower potential, by the way. How much is the change in potential? GH. Is that clear? Is that clear? Is that clear? And according to one formula which I was writing earlier, that potential energy is mass into the, if you keep a mass over there, then into the potential, then according to that, change in potential energy would be, if I keep a mass over here, M, then it will be M times change in potential, which is GH, which is MGH. And this we have been doing from class 9, right? Right, guys? That change in potential energy is MGH near the surface of Earth. Right, people? So in this class, we are wanting to have a better clarity on this when it is not near to the surface of Earth, when it is not only Earth what we are talking about, in general what this means. So we are wanting to have big clarity or better understanding of what was this MGH formula. Okay. And then we are going to go way away from Earth and try to apply the correct formula where the MGH formula will not work. It will simply not work because all the places the field will not be G. It is not going to be G. You cannot be lucky to just take the starting field and do a G into the whole H. You can't do that. Is that clear? Is that clear? So again, coming back to this, by definition, change in potential energy is energy and force. How are they related, people? You tell me instead of me telling you. Because potential energy is a term what we are going to define. Okay. So that I will define, but energy and force, you tell me how much, what is the relation between energy and force?
Sir, so the energy is like proportional to the force, and energy is also proportional to the distance that's covered.
Yeah, if you apply some force on a body, it can change the energy of the body, right? But force and energy is different units, right? What is force more related to is the work, right? Force can do work on a body, and if a work is done on a body, the energy is going to change. That is what you have been learning, right? Change of energy of a body is equal to the work done on the body, right? Right, guys?
Yes.
You can increase the energy by doing positive work, you can decrease the energy by doing negative work, and all those things, right? Right? Is that clear? So by definition, potential energy, one of the energies, by definition, potential energy is work done particularly by one kind of force. What force? Gravitational force. Is that clear, guys? So when we are talking about potential energy, then it is defined as, okay, change of potential energy is defined as work done by gravitational force, and that too negative of it, okay? Negative work done by gravitational force. Work done by gravity, I will just write it in. Okay, is that clear? Is that clear? That's a definition. Nobody can do a thing. In true
Sir?
physics people, they will just not even consider potential energy because they'll say that okay, it is just another force. So why to give it such a special name and all? Okay, they work only with kinetic energy. Okay, internal energy and everything is really the how much is the movement in the body is your energy. From where you are sitting, like you are sitting on the top of 11th floor or 10th floor, it is just giving you a potential energy term which is really useless for a physics guy. I can define my height, the height at which I am sitting over here, second floor, as zero energy level. You can define your is zero energy level. If you drop a pen like this at say 11th floor and I drop a pen fell like this at my second floor, how big a difference it makes? Okay, nothing. So anyways, there is a term introduced. It helps us at a lower level solving questions easily by understanding things easily. So let it be. What is that? Potential energy is equal to negative of work done by gravity. Is that clear? So the whole quest will be that, okay, yeah, we know how to calculate work done. So we are going to calculate work done. From there, we will know what is potential energy change. From there, we will say that potential energy change, and I'll write this delta U, is nothing but for a test mass, if it was 1 kg mass, it is just the change in potential, which is a new term for us. Is that clear? And that is how we are going to get the potential values of the point. Is that clear?
Sir?
So the true story will be a mass left over here. A mass left over here actually goes down due to gravitational attraction. Big deal. That's the true story. But then we are just pushing in a word for our own sake, potential. So what we are going to say is that the body has went down because it wants to go to a lower potential energy state. So we will say that work done by the gravitational force is the change in potential energy of the body. And if we are talking about spots independent of the body present over there, then we are talking about the potential of the space. So potential is defined as mass into V. You remove the mass, you don't have the potential energy, you just have the space. Okay. So that's the story. So before we start working on, okay, let us calculate work done and all. Do you understand what is it? So the whole chapter is on the thing that, oh, if it was a disk, what would have been the potential? Why? Because, okay, if it was a disk, what would have been the E? Then you will do a E dot dx integration, which get the potential and all, because if I multiply with mass both sides, m delta V is equal to m E dot dx, this is nothing but change in potential energy, and ME is nothing but force by gravity, right? This is what we have been doing. This is the work done. This is nothing but work done, right? So this is nothing but what was there in the previous chapter. So now we are going to calculate work done by particularly the force which is called gravitational force, which has got a format of Gmm by r square, that kind of force. Okay. So if we calculate the work done by that, we'll say that is what is the change in potential energy. Okay. And we will say that, okay, there's a new term potential for the point. So potential is change in potential energy. Remove the mass from it, divide the mass. Okay, so that is change in potential. And this is the sequence. This is the only thing which is being done again and again. But the only crazy thing will be this F force is not going to be this for all the shapes of the body. Or the field will not have a format of Gm by r square for all the shapes. It is only valid for a point mass. That the formula is Gm by r square. So for depending on how difficult an entrance exam you are going to write, they will have various kind of shapes of the masses. Okay. So thankfully, 95% of the question comes on a point mass, a solid sphere, and a hollow sphere. And thankfully, the formula Gmn by r square remains same for all the three, provided you are away from the body, outside the body. Thankfully, it's the same formula for all the three. For disk, it is not. For ring, it is not. There are other things. Okay. But then, if it is in the entrance exam, there must be some catch. If you are inside the body, if you are here somewhere, the formula is not this, and hence they try to trap you that you are going to use the formula and get trapped. Okay. If you are inside the body, the formula is not this. Is that clear? That's the only thing. No big deal in the chapter. Is that clear, guys? Is that clear?
So,
Again, repeat. Work done by gravitational force alone, if you find, you get the change in potential energy. Negative. Is that clear? Negative, negative. If you find the work done by force alone, you get the change in potential energy. So if you want to find the change in potential, you divide by the mass, you get the change in potential. Okay. So we can only get change in potential, we don't get actual potential. So for that, this is said that, okay, let us just all agree on one point to be 0. So that when we are calculating a change in potential, if the one point is 0, then the other point is giving you the state of the potential and not the change in potential. Is that clear? So that 0 point could have been calculated as, suppose Hitler was giving the law, then it could have been calculated as the height at which Hitler is living. Okay. But it is not the Hitler who gave the laws and all. So this 0 point is infinity, just as a convention. So that whenever you are calculating a change in potential, then you are calculating the potential and repeat it. Suppose from here to there you go and you say it is 10 meters. What is the location? What is the location? God knows. You don't know what is the location here. If the location was here x, then this location is x plus 10. So that kind of issue, that I know the displacement, but I don't know the location. So suppose you define one of the location to be 0, then it's an easy thing. The displacement 10 becomes the location over here 10. Or that thing is 0, 0 plus 10. Is that clear? So if you start your displacements from infinity and try to calculate the work done, it will give you the change in potential energy, which thankfully will be the potential energy formula. Okay, because you are going from infinity, and therefore you'll see a lot of those integration which I was writing over here. Where is that? This integration is done from infinity to a certain spot. Why are they doing that? They are doing it from infinity to a certain spot, so that instead of getting change in potential, forget about change, they get the direct potential. Okay? Because at infinity it is zero. Okay? So that's the story in gist. Now, if you have to ask anything, ask your doubts because time is over. So I'll just calculate some potentials and some fields in the next class. Okay, and explore more on, if you ask for it, explore more on this formula of change in potential will be minus, change in potential will be minus. If you go along the field for a dx distance, the potential will change by dv amount. Okay, why this integration? Why not the simple delta v is equal to e dot dx, e into x? That's also all right. But we fear that E is continuously changing. If E is changing, if E is not changing, this is all good. If E is changing, you rather do the integration. Okay. And the point? That's
Sir?
clear? Hmm.
Sir?
So we'll do the other format of this also. That if V is given to you, how to calculate the E? So V is a scalar quantity. To get a E, we have to differentiate. If along X we differentiate, then we get EX. If along Y we differentiate, then we get the field along the Y direction. If we differentiate with respect to Z, keeping X and Y constant, then we get the field in the direction of Z, and your net field would be EXI plus EYJ plus EZA. This is like, once we have further clarity on this, we can get to the reverse engineering and differentiate V and get E instead of integrating V and getting E. And then some pretty nasty questions on that can be there. Is that clear? Yeah, ask what you have to ask me.
Sir, I didn't like completely understand what potential is.
Ask. Where we have not understood. See,
Sir,
this spot over here is having a potential. Okay. It is a term we are defining. Is that clear? So there is nothing like you have to, it is it's not like a force which you can feel at all. Okay? It's a term what we are defining.
so but what is
Do you think that at this spot, if I keep a mass, that mass will have some potential energy, which we say that is the energy due to the virtue of the position? Do you think that this mass will have potential energy?
yes, sir?
So suppose the mass was 1 kg, okay? And suppose the potential energy it was over here was 20 joules. Is that clear? Is that clear?
Yes, sir.
So if I keep two masses over here like that, so it is 2 kgs, what do you think is the potential energy of this together now?
Sir, it's twice. I mean, if they're the same mass, then it's
And it's
twice.
40 joules, right? Right?
Yes, sir.
So the potential energy is directly linked to the mass over there, right? More the mass, more is the potential energy, right?
Yes, sir.
Here. But had it been here, will it be the same thing? No, something else, right?
Yes, sir, it'll be something
But it's
else.
not just the mass, it is something at that spot also, right? Because of this virtue of being here, this position and this position are two different positions, right? If the remote is over here, it will not have the same potential energy when the remote is over there, even though the masses of the mass of the remote is same at both positions, right? So there's something to do with the position also, right? Right?
Yes, sir.
When the mass is there, we are defining the potential energy of the mass. When we remove the mass and just talk about the spot, then can we say potential energy of the mass? No, there is no mass. So we say potential of the spot. Is that clear?
Yes, sir. But like,
So
what is like
if
the
20
definition?
joules, if 20 joules was the potential energy of a 1 kg mass over here, or I'll just say, I'll take a better example. If 40 joules was the potential energy of 2 kg mass over there, then 40 by 2, which is 20 joules per kg is called the potential of this spot. So 20 joules per kg. If you keep a 1 kg mass, it gets a 20 joules energy. If you keep a 3 kg mass, it gets a 20 into 3, 16 joules of energy. So that spot has got 20 joules per kg of potential to give a body potential energy when it is kept over there. Are you getting?
Yes, sir. So like potential is like something that is like some a term that we are defining, which is like for example, you said 40 joules, right? 40 joules for like two bodies. So potential is something that is giving the energy. It is something
Yeah.
that's over there that is giving the potential energy.
Yes.
Okay, sir.
If this space was, if they, I'm talking about a spot deep in the space, somewhere far, far away, deep in space. I keep 20 joules over here, it will hardly get any energy. Okay. If I leave that, this guy over here is going to come and smash and do some work. Okay. Destroy a few things. Is that clear? In deep space, maybe it will not even move. Okay. That means that deep space is having very less potential. You keep a 1 kg, 2 kg, 3 kg, it is not that 3 kg is going to get any potential energy. The potential itself is very weak over there. Is that clear? So very
Yes, sir.
strong potential comes at a spot when you are near to some big mass, that means the earth. This spot is having a great potential because the earth is nearby. Okay. So potential at a spot is created by a massive body. Okay. Some other body. Is that clear? Massive or not, but some other body. Not the body which is going to come over there. The body which is going to come over there will get potential energy. This point over here had got potential due to other bodies present. Okay.
Yes, sir.
It's a
So,
region
so
of
like,
it's a
and
region
one
of
more thing,
field. You tell me?
sir, in the like integration formula that you gave like before you stop sharing the screen, you said that in case like E is very,
Yeah.
like in what kind of cases would E vary?
All cases. Like what is the E formula right now over here? GM by R square, right?
Yes, sir.
So if you go a little away, if you are moving, for change of potential, you have to move. For work done, you have to move. Okay. If you are moving, will the R not change?
It will change, sir.
So GM by R square or GMM by R square for 4, the R will change, right? So R will change, so E is changing. Is that clear?
Yes, sir.
So we'll have to actually integrate, okay? So just because we don't want to complicate things, for gravitational field near the Earth's surface, we just somehow say that okay, E is not changing. It is actually changing, but it is changing very, very slightly. So we say please take it constant, okay? So E goes outside the integration. Then it is only integration of dx, which is change of distance. So it is simply the height. So E into x. Is that clear?
Yes, sir. Got it.
Yeah. But when E is really properly changing, and you cannot afford to take it out of the integration, then you can't. On the point?
Got it, sir.
Anything else? Chalo then. Bye bye.